In 2020, the Olympic and Paralympic Games will be held in Japan's capital, Tokyo. Ahead of the Olympics, major urban restructuring is underway. It aims to reinforce aging infrastructure built from the latter half of the 1950s, during Japan's period of rapid economic growth, and to enhance Tokyo's new role as an international city. This large-scale infrastructure construction work is being sustained by state-of-the-art artificial intelligence and information technology. In this program, we are at the front lines with major Japanese construction company SHIMIZU Corporation as it endeavors to redevelop Tokyo. Explore with us cutting-edge technology in the fields of construction and public works. Newly constructed on Tokyo Bay for the Tokyo Olympics and Paralympics is the Ariake Gymnastics Center. With a length of 140 meters, a width of 120 meters, and a height of 30 meters, this building will hold 12,000 spectators. It will be the venue for Olympic gymnastics, rhythmic gymnastics, and trampolining, and for Paralympic bocce. After the Games, the seats will be removed to use the center as an exhibition hall.
Hi, おはようございます。9月19日木曜日、朝礼を行います。少ないと抑えられないということで。
This is Masamichi Nagata, the construction manager of the Ariake Gymnastics Center. Soon, he will have to hand over the building. There is just over a month until its completion. Work has entered the final stages. Nagata carefully checks on the progress being made. He makes a point of speaking directly with the workers.
はい、順調ですか。まっすぐ行ってる。まっすぐ行ってます。なんとか。ちょっともうちょい見ながら、全体的にやってみます。多少直しながら。はいはい。
The biggest feature of the building is the abundant use of wood for the roof and the seats, evoking a sense of tranquility and healing, and creating an image of the venue as a vessel of wood. Wood is also used in the outer walls that jut out diagonally, above the passageways that encircle the venue. Wood scraps are even used in the passageway paving. The aim is to make the athletes and spectators visiting from around the world feel comfortable. The greatest challenge for SHIMIZU Corporation has been how to construct the arch-shaped timber beams that support the roof. Although these beams are 90 meters long, they aren't made of steel usually used for long-span structure. They had to work out how to attach it. With an arch shape, its weight pushes it outward, making it unstable. And in this case, the span is a colossal 90 meters. SHIMIZU decided to adopt a beam string structure. Steel cables were drawn beneath the timber beams, and steel struts were placed between the beams and the cables. In this way, like the mechanism of a bow and arrow, the steel struts cause the arch to push upward. This balances the force of the beams, struts, and cables, which creates stability.
How to construct a space as big as this that's supported by timber, something that is rarely seen worldwide, and how to do that in a construction period of just 2 years. With a scale like this, it generally takes 2.5 years. To get it done in 2 years requires quite a bit of ingenuity. We considered many methods.
Nagata has experience building baseball stadiums and exhibition halls, so he had no hesitation working on a large building. But based on his experience, it would take 2.5 years. When SHIMIZU accepted the job, there were only 2 years left. He would have to cut construction time by 6 months. He fundamentally re-evaluated the construction process. Usually, buildings are constructed from the bottom up. But here, after first completing the floor, they decided to build from the side. If the stadium were cut vertically, you would see a similar structure repeated. Based on that, they decided to start work from the rear and gradually move forward.
With such a big space, if we set up scaffolding for all of it, it would be a huge amount. By building from the back, we can move the scaffolding and the workers can complete one cycle. Because that cycle is repeated, efficiency steadily increased, and in the end, work was done almost twice as fast. We were able to do it in half the number of days.
The beams are factory-made, using domestic larch trees, and are brought to the site where they are put together. By proceeding in order from the rear, the roof could be separated into 5 units and attached in order.
We placed the frame for the unit on the ground floor playing area first, and then we assembled the roof unit on that frame using a crane. This procedure took a lot of time at first, double the amount of time I had estimated.
Assembly of the roof units. How to reduce the amount of time needed to do this subsequently became an issue. Each roof unit is 70 meters long, 14 meters wide, and weighs 200 tons. The floor is already complete. Consequently, a heavy, large-size crane cannot be brought in. So, they use hydraulic jacks to lift them to a height of 30 meters. Slowly, carefully, they raise them. Because the raising of the roof was divided into 5 lifts, lessons learned from the first lift were applied to the second lift, and then applied again from the second to the third, and so on, which rapidly increased the speed of the work.
In the end, it took 1 month to assemble at ground level. The workers' experience also made a big difference to the lifting process, which we completed in half a day.
At first, they worried that processing accuracy with timber would not be as good as with steel.
The accuracy with the timber was amazingly good. There was not even a deviation of 1 or 2 millimeters. The total length of this beam string can be adjusted by pulling the cable. In order to fit the beam between the frames on each side, the overall length must be adjusted. But by adopting the beam string structure, we could construct the roof accurately with timber. Really, as calculated, we proceeded with the timber without any measurement error, and conversely, I thought that it is a more precise structure.
The stadium is filled with the knowledge and ingenuity of all concerned. This wooden masterpiece will be ready for its Olympic performance in July this year. Urban redevelopment is happening all over Tokyo. Huge skyscrapers and other structures are being built where old buildings and houses used to be. This is the construction site of a 40-floor skyscraper with 2 basement floors. The framework of the 5th floor section is currently being built. In the city center, built more than a century ago, the subway has been used for many things, and there is a possibility that unrecorded buried objects have been left behind. Consequently, an advanced geological survey was carried out via boring to check whether any impediments to construction might occur. There were also other issues with this site.
This is a large-scale building, and compared with the site, there is almost no spare space. In these cases, the most difficult part is bringing in materials and putting the building together. Since there is no place to put the materials, we are renting land at a different location and temporarily assembling it there, bringing it to the site, and installing it. I think this site is unique to the city center.
A crane is needed to lift the assembled materials to the work site. Currently, 3 cranes are being used. If conventional tower cranes were used here, there would be an increased chance of the booms colliding. So, SHIMIZU Corporation developed and introduced a new crane. It is the world's first horizontal sliding crane. By expanding and contracting the boom in a horizontal direction, the work radius can be adjusted from 3 meters up to 25 meters. One horizontal sliding crane is being used at this site. It is mainly being used to hoist construction materials and has greatly improved work efficiency. A horizontal sliding crane's maximum load is 12 tons. Compared with a conventional crane, since the highest point of the boom is lower, it works well in areas where aviation restrictions apply. On an 8.1-hectare site in Tokyo city center, a grand project to build Japan's tallest skyscraper, 330 meters tall, has begun. Work started in August 2019. Completion is scheduled for March 2023. This redevelopment project, featuring a building of 64 floors above ground at its center, is the work of major Japanese real estate developer Mori Building. After completion, 3,500 people will live here. 20,000 people will work here, and between 25 and 30 million visitors are expected each year.
Since competition between global cities is intensifying, the question of how to attract people, materials, money, and information will be very important. The Toranomon Azabudai project will be a multifunctional, compact city with international-grade offices, housing, a hotel, and even an international school, creating a new cultural and economic center that will draw active people to Tokyo from all over the world.
SHIMIZU Corporation is developing various robots and pursuing labor-saving initiatives. This robot welds a steel column. Using a laser, it measures the shape of the groove and where to weld, and precisely covers it with welding material. The robot arm has 6 axes, so it moves freely as it welds. Right now, in Japan, the lack of skilled construction site laborers is a serious problem. At its peak, the construction of a skyscraper requires more than 2,000 workers. Securing skilled laborers on site is a huge concern.
We see building on this scale, including securing labor, as an enormous job. Amid a shortage of labor, those of us on site plan to utilize welding robots, unmanned transport systems, and various other methods.
This is a transport robot. Once the material is selected and the destination is entered into a tablet, the robot will take it there. If it encounters an obstacle, it stops and waits. If it does not move for a fixed time, it recalculates the route, goes around the obstacle, and continues on. It significantly boosts labor saving on site. Robots that install ceiling and floor materials are also being developed. They use image sensors and laser sensors to confirm where to place the screws. They screw the materials in the precise spots. The Toranomon Azabudai project plans to use state-of-the-art robots like these at its worksite to boost labor efficiency. In earthquake-prone Japan, earthquake countermeasures are essential. SHIMIZU Corporation has developed a high-performance shaking table that can reproduce the shaking of past earthquakes from around the world. This experiment uses a large-scale shaking table to reproduce the vibration of a skyscraper. The ground and the building shake in a fixed rhythm. This is called a cycle. When these cycles overlap, resonance occurs and the building sways greatly. The cycle that overlaps with high-rise buildings is long-cycle seismic motion. New measures have been devised to counter this. This 38-story skyscraper, with another 3 basement floors, is Tokyo World Gate's Kamiyacho Trust Tower. This building has level surfaces, but because it is rectangular, cycles differ on its short and long sides, producing complex vibrations. To counter this, the building uses a new vibration suppression device, the SHIMIZU Swing Mass Damper. Just one of these devices can absorb the vibrations of 2 different cycles. This is the first such damper in the world. This SHIMIZU Swing Mass Damper is composed of a 380-ton, 12-meter tall, 7-meter wide, and 1-meter thick steel weight, which is on top of the device. 4 legs that are each made of 2 shock-absorbing isolators that are 60 centimeters in diameter and 36 centimeters high. 8 oil dampers. And 2 dynamic screws. The key to creating this groundbreaking vibration suppression device is the dynamic screw. With it, the cycles of the vibration suppression device can be adjusted and the cycles matched to both directions of the building. 4 of the devices have been installed in the space between the 30th and 31st floors of Kamiyacho Trust Tower. During an earthquake, they absorb a maximum of 15% of vibrations, and during strong wind, 25%. The backbone of Tokyo's transportation network is its expressways. New roads are being constructed to improve the city's functions. This is the Tokyo Outer Ring Road, which will connect 3 existing major expressways, the Kangetsu, the Chuo, and the Tomei. The 16-kilometer section from the Oizumi Junction to the Tomei Junction will be joined by a tunnel. It is difficult to construct a new above-ground freeway in the Tokyo area, which is densely packed with buildings and homes. This tunnel's diameter is 15.8 meters. It will become a one-way road with 3 lanes. Construction here will use an excavator called the shield machine and the shield construction method. The machine's diameter is 15.8 meters. It is the largest in Japan. SHIMIZU Corporation is in charge of tunnel construction for a section that runs for about 7 kilometers from Oizumi Junction. The manager of the site is Tadashi Hara. Other construction he has previously managed includes a subway in the city center.
The greatest feature is that the tunnel's cross-section is big. It is Japan's largest long-distance cross-section, so that makes it a tunnel with a high degree of difficulty. This work is a compilation of the shield construction method developed in Japan.
This operation room controls the shield machine. On the front section of the shield machine, the cutter head has teeth 10 to 25 centimeters long set in a radial shape. By turning it, digging proceeds as the soil is shaved away. This is the back of the cutter head. After excavating, a shield jack is pushed into the tunnel wall. When the jack is extended, the shield machine advances. In the space that opens up after the shield machine moves forward, panels that are called segments are assembled in a ring shape to make the tunnel wall. 13 segments make one ring. The segments are carried by a self-propelled cart and are sequentially attached to the wall face. The segments are fireproof in case a fire were to break out in the tunnel, in order to prevent it from collapsing. There is also a unique feature in the way excavated earth is taken away. This site is adjacent to a freeway. A conveyor belt has been set up in a central area of the freeway. It is carrying soil to a temporary storage area about 6 kilometers away.
This is probably the first time in the world that a conveyor belt has been set up on an expressway. This site is narrow. If we were to use a dump truck to take the soil away, we would need one every 15 seconds, which would make the work difficult. So we are following our plan to place a conveyor belt on the expressway.
This construction work at Oizumi Junction will excavate a total of 2.9 million cubic meters of soil. That's equivalent to about 500,000 10-ton dump truck loads. But using the conveyor belt makes trucks unnecessary, and that helps reduce carbon dioxide. The stored soil will be used in public works projects, such as for other road or river works. In order to improve the distribution capabilities of the capital, Tokyo, SHIMIZU Corporation constructed S-Loji Niza, a large-scale distribution facility with a total floor space of 130,000 square meters. The solar power panels spread across the roof generate 2,000 kilowatts of electricity. If a power failure were to occur, they can supply electricity to the facility. A fire detection system that utilizes leading-edge AI technology has been installed in this facility. This is a typical fire alarm that is required by law to be fitted. But, unlike a typical house or building, the ceiling is high, and in the case of a huge space like a distribution center, it can take time for smoke and fire to be detected. A fire at a distribution center in the past burned for 12 days. SHIMIZU Corporation therefore looked at the cardboard and vinyl used as packing material. It developed a special sensing system that promptly detects the chemical substances that these materials release when burned. It is also equipped with a laser sensor that detects smoke, and artificial intelligence comprehensively analyzes various information. With high precision, the system is ready to quickly detect fires and report them. It takes less than 10 minutes for a fire to be detected after cinders are created. That's about the size of a fire that can be extinguished by buckets of water. It is also developing a system that uses AI technology to improve the safety of construction work. This is a site where explosives are used to excavate a tunnel. This is an in-vehicle style 3D scanner. It scans the tunnel's excavation face and analyzes in detail the data of the shape of the excavation surface. It automatically calculates the most effective and safest location for an explosive charge. This data is transmitted to the excavation machine and, based on the data, the sections where explosives are set are accurately excavated. The data related to excavation is all stored, and using AI technology is utilized in subsequent work. At this site, an AI camera and other equipment that monitor the movements of heavy machinery and people are also set up. They carry out analysis to improve work safety and will utilize that in subsequent work.
With the renewal and rebirth of the city, it will become an inclusive city, comfortable for everyone to live in and thrive in, not only for Japanese citizens, but also for foreign business people and those living here. In this way, Tokyo's international competitive power will improve, and that will also lead to great development economically. We in the construction industry do that work reliably, and we feel deeply that fulfilling that duty is a great honor. It is a heavy responsibility, but I believe it is our mission.
Japan's capital, Tokyo, is trying to accomplish a huge transformation as an international city. Underpinning this rebirth of Tokyo is a base of extensive experience and know-how, greatly supported by remarkable progress in construction and public works technology that is making the most of leading-edge AI and IT.